Welcome to calculus.
We've always been good at math. How hard could calculus be?
On this episode, Stevenson will demonstrate
We have the first derivative test to find our local extrema. Well, you can in some instances use the second derivative test to also check your local extrema. Here's how you do it. Step 1, find your first and second derivative. Now this is a polynomial, so I'm going to use power rule. Now, we need to find the critical points of our possible extremas for this function. So I need to use the first derivative for that. Okay, so when does the first derivative not exist? Well, never. It's a quadratic. They exist everywhere, right? Their domain's all real numbers. When is the derivative equal to 0? Well, I'm going to do some scratch work off to the side. So we're going to set our derivative to 0 and solve. Okay, so I do have two choices here, or two possible candidates. But instead of graphing my first derivative now, and then looking at the change in sign, what I can do is I can now take these critical points, these candidates, and test them in my second derivative. That's the second derivative test. And so if my derivative, my second derivative, ends up being negative, if the number result is negative, then that means my graph is concave down and thus it's a maximum. But if I plug in these numbers and I end up with a positive result, that means my graph is concave up and it is a minimum. So I'm going to test these individually. Here we go. So I put 2 into my second derivative and I got 12, which is greater than 0. It's positive. This means f has a local minimum at this value. Now, again, why does it have a local minimum? Because if it's concave up, right, the second derivative at this point is positive, that means it's concave up. So if it's concave up, that value must be a minimum. Let's try the next one. Now in this case, my second derivative was negative. That means my graph is concave down at this point. So that would imply that at this number, x equals negative 2, it would be a maximum. Now to actually find the exact extrema, then I would need to take these values and plug them into the function. So now we can write out a statement, and what we're going to use as our justification is the second derivative. So I'm going to say f has a local minimum of negative 21 when x equals positive 2, because f of 2 is greater than 0. F double prime of 2 is greater than 0.